Euclid was mapping open sky when something in the data refused to make sense. Two objects, further away than anything ever recorded, giving off more energy than 1 trillion suns. Nothing out there is supposed to be that big. Astronomers have spent a month trying to explain them away. The only reason we know they are there at all is that their light arrived stretched almost past recognition. One sits at a redshift of 7.77, the other at 7.69, which means the expansion of space has been pulling their light apart for more than 13 billion years before it landed on Euclid's mirror. Nothing more distant has ever been confirmed. The previous record, redshift 7.64, had stood since 2021. And after all that distance, each one still arrives carrying the apparent brightness of 1 trillion suns. They are also not alone. In a paper published in Astronomy and Astrophysics on the 6th of July 2026, led by Daming Yang at Leiden University, Euclid reported 31 of these things from the same ancient stretch of the universe, 12 of them from its first 700 million years. That more than doubles the number we knew about. Subscribe and stay with this, because the closer we look at them, the worse the problem underneath gets. Here is that problem. Whatever sits at the center of these objects has to be almost unimaginably heavy, roughly 1 billion times the mass of the Sun. And there is a hard physical ceiling on how fast anything can put on that kind of weight. Matter falling inward heats up and radiates, and past a certain intensity, that radiation pushes back hard enough to throttle its own supply. It is called the Eddington limit, and it means the mass can only double about once every 30 million years. Start from the corpse of an ordinary massive star, a seed of perhaps 100 suns. And even if the first stars lit up 200 to 300 million years after the Big Bang, you need something like 600 million years of uninterrupted feeding to reach 1 billion. These objects got there faster than the arithmetic allows. The first time anyone found something like this, they thought it was a message. In 1963, the Soviet astrophysicist Nikolai Kardashev proposed that a radio source catalogued as CTA-102 might be the work of a civilization far beyond our own, a species that had learned to harness the output of an entire galaxy. 2 years later, Gennady Sholomitsky at the Sternberg Institute in Moscow found that the signal was varying, rising and falling, as though something were modulating it. On the 12th of April 1965, the Soviet news agency put it out to the world: contact with a super civilization. For a few weeks, it was the biggest story on the planet. Then Palomar Observatory turned toward CTA-102 and found what it actually was: a quasar, a galaxy whose center blazes because a supermassive black hole is swallowing matter fast enough to shine across the observable universe. That is what Euclid has now found 2 of, older than any seen before. And each one is a black hole that had no time to grow. The difficulty is not lost on the people who do this work. Yoshiki Matsuoka of Ehime University put it plainly: the question of how black holes 1 billion times the Sun's mass could form and grow so fast in the early universe has, with this new distance record, only become more pronounced. And the pressure is not new. Astronomers have been circling it for years. The quasar that held the record in 2021 already forced a strange admission. It sat at redshift 7.642, weighed about 6 billion suns, and was seen roughly 670 million years after the Big Bang, devouring around 25 suns worth of gas a year and driving winds outward at 1/5 of the speed of light. Baigi Wang of Steward Observatory led that discovery, and his colleague Xiaohui Fan worked through what it demanded. Even letting the black hole grow at full throttle from just 100 million years after the Big Bang, its starting seed could not have been a dying star. It would have needed to begin at 10,000 solar masses at least, something Fan described as forming when primordial cold hydrogen gas collapses directly, skipping the business of becoming a star at all. You would expect that finding more of these quasars would help. More examples, more data, a clearer picture, that is usually how a puzzle gets solved. Here, the opposite is happening. It took astronomers more than a decade to turn up the first 10 or so quasars at redshift 7. Euclid found more than that in a single year. Antonio Lamarca, a research fellow at the European Space Agency, noted that the Hall more than doubles the count of quasars we know from that ancient era. But every one of them is another near-billion solar mass black hole with no time to have been built, and pushing the record from redshift 7.64 out to 7.77 does not narrow the gap. It widens it. Each new object makes the timing problem larger, not smaller. So where could that head start have come from? One answer has a name attached to it. The astrophysicist Priyamvada Natarajan spent years arguing that these black holes were never small to begin with, that instead of growing up from stellar corpses, they were born heavy. In her picture, a cloud of pristine gas collapses straight into a black hole of 10,000 to 100,000 solar masses without ever fragmenting into stars, a so-called direct collapse seed. And she made a specific, testable prediction. Such an object would betray itself as an overmassive black hole galaxy, a system where the black hole is freakishly large next to the few stars around it, appearing at a redshift somewhere between 9 and 12. It was a bold claim, running against the rival view that the seed stayed small and simply cheated the speed limit in brief bursts of super Eddington feeding. Then, in 2023, the prediction seemed to walk onto the stage exactly as written. A team led by Kos Bogdan and Priyamvada Natarajan combined X-ray data from the Chandra Observatory with infrared images from the James Webb Space Telescope and found an object called UHZ-1. It lay at a redshift of 10.1, just 470 million years after the Big Bang. The black hole appeared to weigh tens of millions of suns, rivaling the entire mass of the galaxy hosting it. It was heavily shrouded, the kind of Compton-thick source where dense gas absorbs most of the light, and its redshift fell squarely inside the window Natarajan's theory had marked out in advance. For a moment it looked like the cleanest possible confirmation, the heavy seed idea caught in the act. And then, this year, it came apart. In 2026, an independent team led by Zhu and colleagues went back to the same telescopes and reprocessed the full 2.2 million second Chandra dataset behind UHZ-1. When they did, the crucial X-ray signal, the evidence that a giant black hole was hiding there at all, largely dissolved. What had been reported as a firm detection above 4 sigma faded to something between 2 and 3 sigma. The statistical territory where a real signal and a fluke start to look the same. Fresh Webb infrared measurements failed to find the hidden, feeding black hole the first interpretation required, capping any concealed source 1 to 2 orders of magnitude below the original claim. Their conclusion inverts the story. UHZ-1, they argue, is most likely an ordinary low mass. Metal-poor galaxy busy forming stars with no monster inside it at all. The one object that seemed to answer where these black holes came from had just been unanswered, and the case everyone thought was closed was open again. Set the argument aside for a moment and stand next to the record holder itself. The more distant of Euclid's 2 finds is not a quiet point of light. Written into its spectrum, just to the blue side of a line emitted by ionized nitrogen, is a broad trough where light has been swallowed, the signature astronomers call a broad absorption line quasar. That trough is a direct fingerprint of motion, gas being driven off the black hole's accretion disk and flung outward. In the most luminous quasars at thousands to tens of thousands of kilometers per second. This is not something glowing passively at the edge of time. It is a black hole tearing matter apart and blasting the debris into its own galaxy. And we are watching it happen 13 billion years after the fact. It is worth being concrete about what that kind of engine does, because it grounds the word terrifying in physics rather than mood. A quasar's accretion disk, a structure perhaps 100,000 times smaller than the galaxy around it, can outshine every star in that galaxy combined. The most extreme of them pour out more than 10 to the 48 ergs of energy every second. Radiation at that intensity is not just bright, it is corrosive. High-energy photons can pump enough energy into the outer atmosphere of a planet across the host galaxy that the gas simply boils off into space, leaving worlds stripped and sterile. The same winds and jets heat and expel the gas a galaxy needs to make new stars, and can shut star formation down entirely, and we still cannot say where they began. Beyond direct collapse and beyond bursts of super Eddington feeding, there is a more exotic possibility that skips stars altogether: primordial black holes, born in the first fraction of a second after the Big Bang, seeding the giants directly. No evidence singles it out, but nothing yet rules it out. What we do have is more data on the way. Euclid's first cosmology results arrive in October 2026, and its first foundation data release follows in November. So this sample of ancient quasars is going to keep growing. This is where it leaves us. We built a telescope powerful enough to find the first monsters of the universe. And instead of explaining them, it has taken away the one answer we thought we had. We can now see these black holes far better than we can account for them. 13 billion years of travel, ending on a single mirror, the light of something our own equations say should not yet exist. Drop the seed you would put your money on in the comments. And if this was worth your time, a like genuinely helps it reach other people who think this way. Subscribe to be here when the next data release lands.